Hello, my dear students. I hope all of you are fine. So this is the very first time I am making a video on Math 120, and already you know that we have completed integral calculus part, and now this is the time to focus on ordinary differential equation, and this video is totally on the basic concepts of first order ordinary differential equation. So before starting this video, I want to say that be safe, take care of your family, and focus on your study. So here we go. For differential equation, we will follow this book. You can download this book from Google Classroom. From this book, we have to cover these topics. That means chapter 2, 3 and chapter 4 are in our syllabus. Chapter 2 deals with the first order differential equation, and the application of first order differential equations can be found in chapter 3, that is in section 3.1. Whereas chapter 4 deals with the higher order differential equations. So we are starting from chapter 2 now. Before starting chapter 2, you have to know some basic notations, definitions and terminologies regarding a differential equation. So what is a differential equation and what are the classifications of it, you have to know at first. A differential equation may be classified into two categories: ordinary differential equation and partial differential equation. In this syllabus, we have to study only the ordinary differential equation part, but the partial differential equation is not in our syllabus. You can see ordinary differential equation involves ddx, whereas partial differential equation involves del x del y. Now let's have a look on the definition of differential equation. A differential equation is an equation that involves a differential operator ddx, del x or maybe del y. You can see from the examples, all the examples are of differential equation, and the first three are denoting the ordinary differential equations, and the last two are denoting the partial differential equations. Now, what is an ordinary differential equation? A differential equation is called ordinary if it involves ordinary derivatives, that is ddx, and only a single independent variable. So this is called ordinary differential equation. You can see from the examples, dy dx plus 5y equal to e to the power x. So the upper variable is y. This is called the output or dependent variable, and the lower variable, it is x, and this is the input. You can think about y equal to f of x. So here, how many input variables you have? Only one, that is just x, and the dependent variable is y. So we can say that a differential equation that involves only ordinary derivatives with respect to a single input variable, that is called an ordinary differential equation. Whereas a partial differential equation is a differential equation that involves partial derivatives with respect to two or more input variables. You can see from the examples. So here we have independent variable x, independent variable y. You can think about a function with two input variables f of x comma y, and output is suppose g. So how many input variables we have? Two, that is x and y. These two input variables are called independent. So if we need to find the first derivative, we can find by this way: del f del x and del f del y. So for this type of functions, we have to use partial derivatives, and the equations that we will obtain, that will be a partial differential equation. Now we need to understand some important notations. Remember, ddx can also be written as uppercase D. So if ddx is equal to d, then d squared dx squared can be written as d squared, and so on. So the nth derivative can be written as dny. At the same time, here you can see a differential equation, that is dy dx equal to x minus x squared over y cube. So this part, the upper part y, this is called the dependent variable or unknown function, and the lower part x, it is denoting the independent variable. So you can see on the right side that the same differential equation is written in different form. All the forms are of same meaning, but the first one, that is dy dx, this is called Leibniz notation. It is named after mathematician Leibniz. And the second one, it is d notation, and the third one is called the prime notation, and the fourth one is the dot notation. As you know that dy dx can be written in y prime or y dot form. Now we have to know two important definitions, and the definitions are what is order and what is degree. The order of a differential equation is the order of the highest derivative that is involved in the equation, and the degree is the power of the highest derivative of a differential equation. Think about the last example. This differential equation contains both d dt and d cube dt cube. So the order will be 3. Now you can see that this third derivative is raised to the power 4. So the degree is 4. You can summarize that this is a third order 4th degree ordinary differential equation. Now, based on linearity, a differential equation may be called linear or nonlinear. A differential equation is called a linear differential equation if it is of this form. That means it may be of order n, but degree must be 1. At the same time, multiplication of dependent variable y and dy dx is not allowed. Also, power of y should be 1. Whereas a differential equation is called nonlinear if it is not linear. But more specifically, we can say if the degree is greater than 1, or the multiplication of y and dy dx is present, or any kind of nonlinear functions or nonlinear terms are present. You can see 3 examples are given. In first example, the product of y and dy dx is present. In second example, a nonlinear function sin y is present, and in the third example, a nonlinear term y squared is present. Since the power of y is 2, so this is a nonlinear ordinary differential equation. So that means we can say all these are nonlinear ordinary differential equations. Now we are going to focus only on the classification of linear differential equation. So a linear differential equation may be homogeneous or may be non-homogeneous. So what do you mean by homogeneous linear differential equation and non-homogeneous linear differential equation? A linear differential equation will be homogeneous if the right side of that differential equation is 0, and a linear differential equation will be called non-homogeneous if the right side of the differential equation is not equal to 0. You can see Some examples are given here. In the first two examples, the right sides are 0. So these two differential equations can be called homogeneous linear differential equation. Whereas, think about these two examples. Here on the right sides you can see you have function for x. So these two differential equations are called non-homogeneous linear differential equations. So whatever four examples are here, all these are first order linear differential equation, but the first two are first order homogeneous linear differential equation and the last two are first order non-homogeneous linear differential equation. Now you can think about higher order differential equation. So a higher order linear differential equation will be called homogeneous if the right side is 0, and it is called non-homogeneous if the right side is a function for x. Now we have to understand two important concepts. What is an initial value problem and what is a boundary value problem? You can see here two differential equations are given, the first one and the second one. With these differential equations, we have some conditions. Now, if we look on the first differential equation, you can see here we have two conditions given. The first one is y of 0 equal to 1 and the second one is y of 1 equal to 2. Y of 0 equal to 1 means when x equal to 0 then y equal to 1, and y of 1 equal to 2 means when x equal to 1 then y equal to 2. So the value that is inside the parenthesis, this is the value for independent or input variable x, and the value that is on the right side, it is denoting the value for dependent or output variable. So for this example you can see we have total two values, x equal to 0 and x equal to 1. For x equal to 0 we have the corresponding value for y, and for x equal to 1 the corresponding value of y is also given. So that means the boundary is fulfilled. So that's why it is called a boundary value problem. So that means we can say this is a second order differential equation, but we can also say now that this is a boundary value problem. So now we have to focus on the concept of initial value problem. So here you can see four examples are given. All these four examples are for differential equations. With all these four differential equations, we have only one condition. Think about the first problem. This is a first order first degree differential equation. With this differential equation you have only one condition, y of 0 equal to 1. That means when x equal to 0 then the value of y is 1. So you can see only initial value is given. So this is called an initial value problem. This is a first order first degree differential equation. We can also say this is an initial value problem. After initial value and boundary value problem, I think this is the time to discuss about what is a solution. Think about this algebraic equation. 2x plus 3 equals 5 and the solution is x equal to 1. X equal to 1 is called the solution of this equation because if we input x equal to 1 in left side, you will get the right side back. So we can define a solution by this way, that a solution is the value of the variables for which left hand side and right hand side are equal. You can see for x equal to 1, since left hand side is giving us 5 and it is also same as the right hand side, so x equal to 1 is the solution, no doubt. So like algebraic equation, differential equations are also one kind of equation. That means it has a solution. But the only difference between an algebraic equation with differential equation is that the solution for algebraic equations are number, but the solutions for a differential equation is always a function. That means we can define a solution for an ordinary differential equation in this way. That is, a solution is the function y equal to f of x for which left side of the differential equation is equal to the right side of that differential equation. You will understand this concept if you have a look on this question. So here you have a differential equation. At the same time, an unknown function y equal to x square plus 6 is given. And the question is, show that this is the solution of this differential equation. How to find the solution of any differential equation I will discuss later, but for the time being, suppose y equal to x square plus 6 is the solution for this differential equation, and we have to show this. That means if we input this function here, so left side and right side must be equal, and the problem is solved here. You can see, so the left side of the differential equation is dy dx negative 2x, and now if we input y equal to x square plus 6, then the derivative of x squared is 2x and derivative of any constant is 0. So 2x negative 2x is becoming 0. That means what we can say, since left side and right side are equal for y equal to x square plus 6, so this is the solution of this differential equation. Similarly, you will find two more problems on verifying solution in this slide. I suggest you have a look on these slides. You will understand that any solution will satisfy a differential equation. At the same time, I want to say that the solution of a differential equation may be classified into two categories: general solution and particular solution. A general solution always contains constants, but with the help of initial value problem or boundary value problem, we can remove that constant and that solution will become a particular solution. Have a look on this example. This is a differential equation. It is also called an initial value problem because an initial condition is here. So, if we target for the solution of this differential equation, then the concept of integral calculus will be helpful. You know that any indefinite integral will give us an antiderivative with a constant c. So this is how we have found this solution. So this solution is a general solution because it involves a constant c. But with the help of this initial condition, that means when x equal to 2 and y equal to 4, we can eliminate this c. That means c has become 0. So therefore it is now the particular solution. So y equal to x squared is the particular solution and y equal to x squared plus c is the general solution. That means we can summarize by this way: a general solution always contains a constant and a particular solution can be found after removing that constant with the help of initial value or boundary value. Now we have to focus on the format of solution. So a solution can be expressed as in these two forms. It may be in implicit form or it may be in explicit form. Implicit form means f of x y equal to 0 and explicit form means y equal to f of x. You will understand this concept if you focus on this particular solution. It is already in y equal to f of x form. So that means it is in explicit form. But the same result we can express in implicit form. That means if we transfer x squared on the left side, then it will become y negative x squared equal to 0. So that means what you can say now? It is of f of x comma y equal to 0. That is defining that this solution is written in implicit form. Now I think by the time you have learned all the basic concepts regarding differential equation, so this is the time we should start chapter 2, and chapter 2 deals with first order ordinary differential equation. So a first order ordinary differential equation may be of these types. It may be a separable equation. It may be called a linear differential equation. Sometimes it will be an exact differential equation. It may be homogeneous differential equation. And lastly, we can say a differential equation can be a Bernoulli equation. I would like to mention here that if we have a homogeneous differential equation or a Bernoulli equation, then just to get the solution of that differential equations, we need an appropriate substitution. So that's why these two methods are called substitution methods. On the right side box, you can see different notations regarding a first order differential equation is given. Say the first one is y prime equal to f of xy, or it is same as dy dx equal to f of xy. A differential equation may be of this form, which is a first order, m dx plus n dy equal to 0, where both m and n are function of x and y. A differential equation may be of this form also, that is dy dx plus py equal to q, where p and q both are function of x. We have a similar notation just like this equation, and this is here. You can see dy dx plus py equal to q y power n, but the condition is the exponent that we have in this equation n, that can't be 0 and 1. So all these 5 notations are the first order differential equation. That means a differential equation may be of any of the 5 forms from 1 to 5. So once we have a first order differential equation, then we have to know how we can solve that first order differential equation. So a first order differential equation may be separable, linear, exact, homogeneous, or a Bernoulli, and it will take any of these 5 forms. So now we are targeting for the methods how we can find the solution. Now we are starting from a separable equation, and we are targeting for the solution of a separable equation. But the first thing first is that we have to recognize whether a differential equation is separable or not. We will understand a separable equation if we have this form, that is dy dx equal to f of x times g of y. This is called the standard form of a separable differential equation. So suppose we have a separable differential equation, and just to find a solution we need to follow 2 steps. In step 1, you have to make a group of f of x with dx and g of y with dy. Once the grouping is done, then you have to integrate both sides in terms of x and y. Then by integrating you will get the general solution. Remember, with general solution there will be a constant c. If initial value is given, then we can also find the particular solution by eliminating c. Now suppose you have a first order linear differential equation. So we need to know how we can find the solution of that first order linear differential equation. At first, we need to know the standard form of a first order linear differential equation.
and it will be always in this form, dy dx plus py equal to q, where p and q both are function of x, and this is called the linear equation. So if we have a first order linear equation, then we have to follow these three steps to find the solution. In step 1, it is written that confirm the standard form at first. It means sometimes you will find a differential equation that will be not in standard form. So you have to convert that inconvenient form to the standard form. That is defined in step 1. In step 2, we have to find one quantity that is called integrating factor, in short IF, and IF or integrating factor is defined by e to the power integration p with respect to x, that is e power integral p dx. After finding integrating factor IF, we can directly find the solution, and the solution will be y times integrating factor equals integration of q times integrating factor with respect to x, and there will be a constant plus c. You will find p and q from this standard form. This is how we can find the solution of a linear differential equation that is of first order. Now let's see how we can recognize an exact differential equation and how we can find the solution of an exact differential equation. So an exact differential equation will always take this standard form, m dx plus n dy equal to 0, where m and n both are function of xy. And this differential equation will be exact if it follows this property, that is del m del y equal to del n del x. That means the first partial derivatives are same. So that differential equation will be called an exact differential equation. Suppose for some problems del m del y is not equal to del n del x, then this differential equation will not be exact. That means a differential equation will be exact if it follows this property. So this is how we can recognize whether m dx plus n dy equal to 0, that means a first order differential equation is exact or not. So now we need to target for the solution. For this again 3 steps will be followed. In first step we have to confirm the standard form m dx plus n dy equal to 0, and then in step 2 we have to check whether it is exact or not by using the partial derivative, and suppose it is exact, then the solution can be found by this process, integration of m dx plus integration of n with respect to dy equal to a constant c. But there is a condition here, whenever you are integrating n, that will not contain any x term. You will understand what I am saying if we solve one problem, but for now try to understand or remember this concept. So this is the process how we can solve an exact differential equation. Already I have discussed the solution technique of a separable equation, linear equation and exact equation. Now we need to focus on how we can solve a homogeneous differential equation and Bernoulli differential equation. Already I have mentioned that homogeneous differential equation and Bernoulli differential equation are known as substitution process. That means both of these differential equations will take an appropriate substitution. At the same time, I want to mention that if we have a homogeneous differential equation, then we need to convert that homogeneous differential equation to a separable differential equation by using an appropriate substitution. At the same time, if we have a Bernoulli equation, then we need to convert that Bernoulli equation to a linear differential equation by using an appropriate substitution. So before starting homogeneous differential equation, I want to mention that don't be confused with the previous definition that we have learned. See here, it is also homogeneous and non-homogeneous. So this homogeneous is totally different with homogeneous differential equation. It is the classification of linear differential equation. A linear differential equation will be homogeneous if the right side is 0. But whatever differential equation we have here, that is a first order homogeneous equation. So before starting homogeneous differential equation, I again request you, don't be confused with linear homogeneous differential equation with this part. It is totally different from that concept. So a homogeneous differential equation may take this form, that is dy dx equal to f of xy, but this f of xy will be a homogeneous function. So now we have to know what is a homogeneous function. Have a look on the next slide. So a function will be homogeneous, that means a function f of xy will be homogeneous if in the place of x we input tx and in the place of y if we input ty, where t is any constant. Then if we get t power n and the main function back, then that function f of xy is called a homogeneous function. So since this function is homogeneous, we can say this is a homogeneous differential equation. So don't be confused with the previous concept. That was a linear homogeneous differential equation where the right side is 0, but here on the right side we have a homogeneous function of degree n. You can see this is degree n. So I think it is getting difficult to understand. That's why I have come up with an alternative condition. So you don't need to check this one, you can check this process. So I am going to demonstrate the alternative condition. This is the alternative condition to check whether a function f of xy is homogeneous or not. So a function f of xy will be homogeneous if the powers of all terms are same, or if the sum of the powers of the product terms in that function are same. Then f of xy will be a homogeneous function. You will understand from these three examples. So in first example, we have dy dx equals y negative x over y positive x. That means this is a function of xy. So now we can have a look on the powers of every terms. Here y power 1 x power 1, y power 1 x power 1. So that means since the powers of all terms are same, so this is a homogeneous function of degree 1. So that means this is a homogeneous differential equation. Similarly, we can check the second example. Here you have y squared plus yx dx negative x squared dy. So in this part you can see the first term with y squared, it is of x squared, that means power is 2, and the product of yx with power 1 plus 1, that is 2. So that means all the terms that we have here are with or power 2. So that means it is of homogeneous function of degree 2. So this part is important. Here we have a product term yx. So have a look here. If the sum of the powers of the product terms are same, that means here we have 1 and 1, y power 1 x power 1. If we sum up these two, then you will get 2. So that means that is same as x power 2 y power 2. So this is a function for degree 2. That means this is a homogeneous function. Similarly, I have added another example here. You can see x squared dy dx equal to y negative xy. Let's see whether it is homogeneous or not. So first of all, x has power 2, but here y has power 1. So that is a contradiction. All the terms should have the same power or degree. So since it is a contradiction, we can say this is not a homogeneous differential equation. I hope you understand. Suppose you have a homogeneous differential equation that is of the form dy dx equal to f of xy, and I have mentioned this equation as equation 1. So I have mentioned earlier that if we have a homogeneous differential equation, then it takes an appropriate substitution, and the substitution will be always y equal to vx. So once we input y equal to vx, then we have to find dy dx, okay, by using the product rule of differentiation. You know what is the product rule? That is d dx of uv. If we have this one, then the result will be u ddx of v plus v ddx of u. So just to find the solution of this homogeneous differential equation, we have to follow total 4 steps. In step 1, find dy dx by substituting y equal to vx and replace y and dy dx in equation 1. Then you will get a function for f of x and a function for f of v. That means after making this substitution, the homogeneous differential equation will become a separable differential equation. Okay, and you know how we can solve a separable differential equation. That means we have to make a group of f of x with dx and group of f of v with dv. If we can do so, then we have to integrate on both sides in terms of x and v, and you will get the general solution. But the solution is still incomplete because you have found a solution for v, but v is not in this given differential equation. Whatever we have here, it is for y. So that means since you have used y equal to vx, so from this part you can write v equal to y by x. That means in the general solution, just replace v as y by x and you will get the proper solution. And finally, a first order differential equation may be called a Bernoulli differential equation. So we have to know what is the standard form of a Bernoulli differential equation. That is, it is of dy dx plus py equal to q y power n. But the condition is this n cannot be 0 or 1, but it is valid for other values. At the same time, here p and q both are function of x. So just like homogeneous differential equation, Bernoulli differential equation also takes an appropriate substitution, and the substitution is y power n equals v. And then we have to use the product rule of differentiation and you will get this part. So after all these things, that Bernoulli differential equation will become a linear differential equation. And you know how we can solve a linear differential equation? That means we know just to solve a linear differential equation we need an integrating factor. An integrating factor that is denoted as if in short, and it is defined by e to the power integration of p in terms of x. Okay, so then the solution will be v times integrating factor equal to integration of q times integrating factor dx plus a constant c. But here remember, we are getting the solution for v because we have a differential equation for dv dx, but v is not in our main equation, so we have to replace v by y power 1 minus n again. That means finally you are getting the general solution. So whatever I have said here, you will get the same thing again in step 1 to step 5. Have a look here. That is, in step 1 it is mentioned confirm the standard form at first. We have to confirm that we have this Bernoulli differential equation. And then in step 2 we have to multiply this one. That means whatever term we will get after differentiation, that means before dy dx, you will get a term that should be multiplied with each and every terms, and then automatically the given differential equation will be converted to a linear differential equation for v. Then after finding the integrating factor just like this way, you will get the solution for v, and finally we need to replace v as y power 1 minus n again. You will get the final solution. So this is how we can solve a Bernoulli equation. So I have described all the solution techniques for separable differential equation, linear equation, exact equation, homogeneous equation and Bernoulli equation. Now it is your task to solve from the homework portion, and you know that I have already given an assignment on all these topics. Okay, see here, some problems are separable, some problems are for linear differential equation, some problems are for exact differential equation, and then you can see homogeneous differential equations are here, and finally 3 problems are from Bernoulli differential equation. You have to know how these problems can be solved. Already I have discussed the theoretical concepts. So finally I want to finish this video just to have a respect to the Bernoulli's family. Okay, so have a good time. Bye bye.